right, we'll get started and welcome to today's session on new generation low carbon geopolymer concretes. And for those who don't know me, my name is Olivia Wu. I'm the chair of the Engineering Solutions session. It's really awesome to see such a great participation from all of you here. And I believe this forum is such a great platform for us to come together, share insights, experiences, and also explore innovative solutions in concrete. I think with the diverse perspectives and experiences that we all bring, this platform will continue to help us stay on top of the industry trends and needs, and also accelerate the development and adoption of new engineered solutions and technologies in concrete. Let's dive into today's topic. As we know, geopolymer concrete offers huge potential to reduce carbon emissions and has shown promise for many years. A new generation material is demonstrating better results, especially for precast applications. So today's session brings together experts from University of Technology Sydney and Canenviro Innovations to share their latest finding. A little bit about the background. This COP session was born from the work that has evolved out of a SmartCrete project, sustainable and fit for purpose concrete materials for construction of assets. And can't wait to hear more from our fantastic speakers today. Before we get started, just a few quick housekeeping reminders to make sure the session runs smoothly. First of all, please stay on mute during the presentation to avoid background noise. And then also we'll have a Q&A session at the end. So please hold your questions until the end. However, feel free to drop your questions in the chat anytime, and I'll get to them during the Q&A session. All right, let's dive in. It's my pleasure to introduce our first speaker, Dave. A little bit about Dave. Dave holds a Bachelor in Chemistry and PhD in Polymer Chemistry from Birmingham University in the UK. He has extensive global leadership experience in the chemicals industry, and having served as the worldwide business head for Siva Specialty Chemicals and based in the USA, and also overseeing sales of over $150 million USD, including a strategic joint venture with DuPont. Dave also served as general manager for Albright and Wilson Australia, managing operations within with more than 75 million Australian dollar in sales. And in 2015, he founded Canenviro Innovations with a vision to develop environmentally friendly products for the construction industry, and combining his deep technical expertise with a strong commitment to sustainable innovation. So let's welcome Dave to present his work.
Thank you very much for that introduction, Olivia. I'll share my screen. Is that okay?
Yes.
Okay. We've been involved in trying to create, superior environmental products for the construction industry since 2015. And we have two arms to our business. The first one is we founded in 2015. We're passionate about innovation. And we have two products. The first one is CAMproof, which I don't intend talking about today. It's a waterproofing membrane for internal and external use. And the one I'll be concentrating on today is a Geomix, which is a patented binder for the production of concrete without the incorporation of any cement. We see this as a next generation geopolymer technology. It's very low carbon, and we tailor make this to suit the specific project requirements of our customers. We offer bespoke systems for a particular set of waste streams available to our customers and for what type of product they want to produce. Our systems work under a geopolymerization, which is very different mechanism from the standard Portland cement concrete. And we have 0% of cement in our formulations. We use a variety of waste streams. We use the traditional products of fly ash and ground blast furnace slag, which a lot of other companies use. But we also use a variety of different slags from steel making, basic, steel, Roth slags. We use a completely different variety of fly ashes. We use mine tailings, and we've used red mud from bauxite processing. So any waste stream which has metal oxides, principally aluminium and silicon oxides, in the right physical form, we can use in our technology. We use both liquid and powder activators, depending on what people want to use in their production plants. Obviously, from the variety of waste streams that I've described, is we not only are improving the environmental performance of the concrete formed, but also we're improving the circular economy because we're using waste streams which would normally have been landfilled. We've seen both in laboratory and in field trials that we can produce comparable results to cement-based concrete. Now, geopolymer concrete in the past has had a fairly negative name from the requirement of using things like caustic to boost the performance of the concrete. We do not use any caustic, and we do all our reactions at room temperature. The silicates we use have a similar HS&E profile to cement, and therefore we offer an improved HS&E position because we're using about 1/10 of the cement used in the form of our activators. Our concrete looks, performs, and behaves very much like traditional concrete. So this is a pour we were doing up in the northwest of Australia. This is a geopolymer concrete based off on a slag. You can see the flow characteristics. You can see the ease of finishing on the top of the side there. And it behaves under vibration exactly the same as a cement-based concrete. Okay, what are the technical capabilities and advantages for the precast market, which we're particularly designed in this presentation around today? As I've said several times already, this is a cement-free binder system, which gives a lower carbon footprint. And I'll give some figures later on in the presentation of the relative values. We do all our reactions at room temperature, and we've done pours anywhere from 15 degrees centigrade up to 40 degrees centigrade. You can use seam curing with this system, but it's not necessary. We can achieve very high early strength development. We recommend over 12 MPa in one day. And Kirk will touch on the reasons why we probably need slightly lower one-day strength than traditional cement-based concrete. And it's due to the bond strength between our geopolymer concrete and the reinforcement steel in the system. We have a much stronger bond strength. And we've demonstrated this by lifting 3 metric ton beams with a one-day strength of 12 MPa within 24 hours. Strength development is not an issue for us if the project requires. And we can demonstrate slump retention beyond 60 minutes if required. We can also shorten that to 15 minutes or less if required. It's a very, very adaptable system. And we are proving in collaboration with Sydney University as part of this same CRC Smart Creep that we offer improved resistance properties to acidity, to chemical and salt attack. So there's obvious market opportunities for those results. As I've said, we do all our reactions at ambient temperatures. There's no caustic contamination. We have done our trials in existing cement-based concrete plants, and we've shown that the performance is not adversely affected by cement contamination. Actually, there are some beneficial effects in one-day strength of having small percentages of cement around. Okay, here are some of the figures for production of CO2 per meter cubed. And I've taken this from some work done by Jason Chandler, who is very important in our development activities in this field. A typical, and obviously these figures vary for the particular site, particular geographical location, but this just gives you a general feel for the reductions which we can achieve in the CO2 emissions. For a sole cement-based system, you're around this 434 mark, kilos of CO2 for a 40 MPa system. When you substitute some of the cement with slag, this drops to around 323. And with our system, we're at the 142 mark. This is very dependent on the amount of silicate we use in the mix design. The lower the silicate, the lower this value. We've had a lot of success operating at very low silicate levels below 1.5% of the total concrete. That gives you a lot of advantages in CO2 emissions, in cost, and in the stickiness of the concrete, which is often associated with geopolymer concrete. We see very similar finishing characteristics when you achieve this low silicate level. There is very minimal capex requirements for this technology. The only potential requirements are additional silos to handle the silicate and supply into the batching plants. We do this in existing concrete batching plants, and we're demonstrating this across a variety of situations. We use the same sand and aggregate composition as traditional concrete. We are only replacing the binder, which is why this is so easy to integrate into existing concrete plants, and we are cost competitive to Portland cement-based concrete. This is quite system and geographically dependent. In some cases, we come out cheaper, and some cases we come out slightly more expensive. The key is to lower the amount of silicate in the system. We've used this in conjunction with a multinational mining company where they had a wish to use some of their tailings. For you who are aware of the issues associated with the mining in Australia and worldwide, one of the biggest issues for mining companies is tailings management. So any incorporation of tailings into a finished concrete product enhances the opportunities for more mining. We've worked with multinational concrete suppliers who have a wish to principally use this technology for precast customers. We've worked with independent concrete suppliers in both New South Wales and Victoria. And we are also working internationally, principally in the Brazilian market, with a very large multinational there, who are the second biggest cement supplier in the Brazilian market. We are interested in developing relationships with customers in the precast market. Our business model is to discuss waste streams available to those companies, to do internal work in our laboratory to establish mixed designs which meet the performance of the concrete required in the precast, whether that's a short slump retention time, whether that's a prolonged retention time, whether they want to use powdered silicates, liquid silicates as the activator. We have a strong relationship with UTS. It has benefited us enormously going forward. Kirk will be presenting the technical results today. Unfortunately, due to NDA considerations, we can't discuss a lot of our field trials. But what I can say is what Kirk is seeing in the laboratory, we have seen when we've gone to the field. We want to be seen as the provider of low carbon precast concrete. And we want to be part of meeting Australia's requirements in achieving these low carbon positions. Here's our contact details. Adam is our commercial manager. I'm the managing director. We welcome contact from anybody about ideas about how they'd like to work together. And I'll hand over to Kirk to handle the technical part of this presentation.
And thank you, David. Thank you, Dave, again for the great insights, especially on the technical capabilities and advantages for precast. And now let's keep the momentum going. And I'd like to welcome our next speaker, Kirk, from the University of Technology, Sydney. A little bit about Kirk. Kirk is the project lead and chief investigator on multiple CRC and ARC funded initiatives focused on developing low carbon, durable precast concrete systems with next gen binders. With 35 years in the concrete industry, including 15 in the field and extensive involvement in precast, Kirk brings deep practical insight to research that bridges materials innovation, structural performance, and sustainability. His work targets enhanced durability, reduced embodied carbon, and circular construction through advanced cementitious technologies. He has secured over $6 million in research funding and authorized more than 140 publications, and he has delivered research outcomes that inform national standards and accelerate industry adoption. As a result-driven leader, he works closely with industry, government, and research teams to deliver real-world impact. So please join me in welcoming Kirk.
Thank you very much, Olivia, and thanks, Dave, for covering the earlier part. I'll just share my screen. Lovely to see you all here today. I recognise a few faces. It's been a long time, so welcome. Okay, I like to go through my particular part, which covers the work that we're doing at UTS. As Olivia mentioned earlier, this is part of a larger project that's fit for purpose concrete that's run by the University of Sydney. And at UTS, we have quite an extensive team. Myself, we have Dr. Aziz Mahmood. We also have Miran Shirani, which is the PhD researcher. We have Dave, which you've met earlier today, and also Adam. We have Jason Chandler, and we also have Honorary Professor Vijay Ari Aratni, who's joining us from University of Sydney as well as a chief investigator. And you can see the partners that we have here. We're not only working with Canenviro Innovations, Concrete Insights in the University of Sydney, but Transport for New South Wales, particularly Harish, who's joined us today, and also the Smartcrete CRC. So we would like to thank them for their contribution as well. So today, I've got a little bit of a different spin in terms of this project. Originally, we were seconded to do work on specialty concretes. And as part of that particular process, we took on the work around exploring geopolymers, the sort of new generation formulations that are available from Canenviro, and particularly the Geomix mixes. Just to recap some of the findings that were shared earlier by Dave in terms of field trials. So 4 very unique areas when we look at obviously this technology to be used in the precast market. When we look at fresh properties and curing, what we're finding is that we're able to adjust the workability window there, and we're able to provide enough retention time in the product to suit different needs and different project requirements. The curing process is very, very simplified because of the requirement of less heat due to the geopolymerization process that Dave mentioned before. And as a result, we've got less risk of any thermal cracking, particularly when we're looking at mass concrete applications, particularly around precast concrete girders, super Ts, T-ROFs, etc. When we look at strength and volume stability, one thing going for this technology is it has a very high early age strength, which enables to be able to demold or strip, obviously, your members much, much quicker, and also to handle them, particularly around, say, tilt panels and lifting them, as Dave mentioned before from field trials, that there is enough adequate strength early on. There is also very, very good bond strength, and we're about to embark on undertaking some tests in this area at UTS. And the really good thing about this is that you can ensure that you get much better anchorage for applying, obviously, post-tensioning or pre-stressing much earlier. So instead of waiting for 3 or 4 days, you can apply it, say, between 1 and 2 days if required. Overall, we're also finding that there's less dry and shrinkage, and this is all compared to conventional ordinary Portland cement systems using different binary and ternary blends. In terms of durability performance, we've done some work on ASR, alkali silica reactivity, and aggregate expansion. We're finding that the geopolymer product is performing on par with fly ash blends and also slag blends, both binary, ternary, for mitigating ASR. There is exceptional resistance to chloride penetration, a little bit better than conventional ordinary Portland cement systems. One real key thing going for this technology is there's no delayed ettringite formation because there's no sulfate balance or sulfate depletion required in terms of ordinary Portland cement hydration. And very, very good resistance to acid attack, particularly for sewer applications. And as Dave mentioned earlier, I mean, there's a lot of sustainability and safety aspects. There's less embodied carbon because less heat is needed for curing. So a very important aspect in the precast market. When we look at life cycle assessment, there's a very low environmental impact, including the environmental product declaration forms that accompany the LCAs, and much easier handling compared to the technology a few years ago. As Dave mentioned, it's non-caustic compared to other alkali activated technologies. So just sharing some of the results, and just bear with me as I explain here what we have in front of us. So we've got some isothermal calorimetry plots, which are showing us the heat flow on the y-axis versus time. And these give an idea of the hydration of the system. And what we've done in this particular experiment is we've compared against conventional ordinary Portland cement, a sort of research type binary blend, and also a commercial ternary blend that has both fly ash and ground granulated blast furnace slag. And what you see, whether you cure at ambient conditions of 23 degrees Celsius or you actually cure at a little bit higher temperature, what we're actually seeing is that there's less heat evolved in the system as we move forward with time. There's also a little bit of retardation, but the most important thing here is that we don't really see any sulfate balance or depletion points that occur within the geopolymer systems. So a lot of these sort of findings that I mentioned up the top here have been summarized earlier, but just very quickly, you can see that there is less risk of the DEF occurring in the system, delayed edge and bite formation. As I mentioned earlier, there's less thermal cracking present. And if we actually increase the ambient temperature, we see that the peak behavior sort of comes more in line with a conventional ordinary Portland cement system, but there's some retardation that's present. So overall, the technology seems to be far more appropriate for releasing less heat and requiring, obviously, heat input in the system. So this particular slide covers a little bit more of the fresh properties. We've done some work in mortars. We've also done work in concrete, but I'm just showing you a sample of some of the more comprehensive and collective set of results that we have here. And what's really interesting to note is the retention around basically these systems in mortars. You can see that the powder activated system and the liquid activated system, this is just a variation in the formulation. We've got a few different liquid activated systems that we're working on in parallel. But if you look at the powder activated system and the liquid activated system, I mean, the retention is very, very good. And if we compare against conventional, like 100% Portland cement, shrinkage limited cement systems, our binary blend and ternary blends, you can see we actually do get a loss in retention. So the retention of the geopolymer system is very, very good in comparison to the conventional system. The thing that Dave mentioned before, if we just move over to the right, is the excellent early age strength that we get. And when we see the cluster here, the orange, purple, the blue, we can see that these geopolymer systems, powder activated, a liquid activated system, a different variation 2 versus variation 1, we see that basically these strengths here are much higher than the conventional systems here. And particularly if we're looking at a low carbon concrete, a ternary blend that has 25% fly ash and 25% slag, the strengths that we're getting here after 1 day are almost in excess of 2 times higher than our conventional systems, which is very good. Also, there is very good strength gain moving from 1 across to 7. So 1, 3, and 7 again, compared to the conventional Portland cement systems. And all our testing has been done in accordance with the various Australian standards and equally between mortars and concretes. Just moving forward with a few other results, again, an example of some of the results that we have here is volume stability, looking at dry and shrinkage. I've incorporated Transport for New South Wales B80 limits, which is the Bridges specification for concrete works. And you will see that for a conventional sort of 100% ordinary Portland cement system, that we're somewhere close to the limits, but when we look at a powder activated system, we're actually getting a little bit less dry and shrinkage overall, again, over a number of weeks. I mentioned earlier about the opportunity of using this technology to mitigate ASR. So this is the accelerated mortar bar test. It's an expansion test. It's a rapid screening test. These dark sort of dots here, the blue type dots represent just a standard 100% ordinary Portland cement system. And when we start introducing fly ash into the blends, whether it's a binary or ternary blend, you start to see that the liquid activated and the powder activated systems are performing on par. So we will continue to monitor this expansion up to 21 days, and beyond that, we'll take it right out to 56 days to see what happens with obviously the mitigation around expansive aggregate. So in this particular test, just clarifying that we have used a reactive aggregate that's prone to expansion. We've also done some cement contamination studies because we realize in terms of concrete supply that there may be some cement left over in the silos. And so we've done some studies with 1% contamination and 5% contamination, and the results are pretty impressive. I mean, the flow is still adequate. The retention is there. This is in mortars. Again, we will extend this work to concrete to just to verify the performance. And again, our strengths are quite impressive. They're not really impacted by the presence of the Portland cement in the system. So again, we get similar retention times. We get a higher one-day strength, about 1.5 to 1.8 times higher than the conventional cement systems, the binary and ternary blends, and we get the same 3 and 7 day compressive strengths. So it's pretty impressive technology. So I thought I'd just, in terms of results, maybe just end on this particular slide, which just gives you an overview of some of the comparative features between a powder-activated geopolymer concrete system that we've trialled at UTS versus a liquid-activated geopolymer system versus a ternary blend. And you can see some of the advantages here highlighted. Much higher 3-day compressive strength compared to a conventional system. We get a much higher 7-day strength compared to the 28-day strength, 78% versus 61%. Much higher strengths around the 28-day compressive strength. We're also able to meet flexural strength requirements of Transport for New South Wales R83, which applies to pavements. And a drying shrinkage, as I mentioned before, is pretty impressive. In fact, it's much lower than a sort of conventional ternary blends. The chloride penetration, whether we're doing the Nord test 492 or 443, whether we're doing chloride penetration, chloride diffusion, these results, particularly the 443 result, is very impressive. 0.55 by 10 to the minus 12 compared to 4.21 by 10 to the minus 12. The ASR risk is very low. Expansions are less than 0.1% after 10 days. As I mentioned earlier, the risk of DEF is mitigated when using a powder or liquid activated GBC system. So what's next for us at UTS? I mean, we're only 1.5 years into this project, and we're quite excited that we've got another 1.5 years to go before it completes. And we are wanting to move forward with, obviously, doing some of the work and validation within concrete. We also want to investigate the bond strength. So we've got, currently we're setting up rigs to do this particular test to see if we can apply pre-stressing and post-tensioning much earlier. We want to understand accelerated and natural carbonation behavior. We want to be able to assess the carbonation depth, the rate, and the buffering capacity of the geopolymer technology. We're very keen to partner with National Precast Concrete Association of Australia members to upscale the technology and monitor the performance, which means that we're moving from this technology readiness level of 1 and 3, which is what we're doing at UTS, really showing the demonstration in the field with low-risk field trials. And importantly, we recognise the importance of Ausro's specification, APT 329-17, which is sort of produced by Ausroads around the use of geopolymer technologies and some of the guidelines. We want to work with the specification and also Standards Australia Technical Specification 199 to be able to work with the precast manufacturers to seek endorsement of, obviously, the technology meeting the various limits and specification requirements. But we do also realise that there are certain test methods that we're working on to get a much better understanding on how to measure the performance of geopolymer products. So my final slide here is just giving you an idea of various different application areas in terms of precast. I know a lot of you here online would be very familiar with all these different technologies, but we can meet structural and non-structural applications in terms of what we use the technology for. So that's it from me, Olivia, and thank you very much for the opportunity to present this exciting project and the technical data that we have today.
Appreciate it, Kirk. And thank you again to our speakers, Dave and Kirk, for sharing this great project work and insights. Now we'd like to open the floor for questions, and I encourage you all to ask questions and make the most of this platform. Please drop your questions in the chat and I'll read it out. And if you'd like to ask a question yourself, feel free to raise your hand as well. Okay, we have a question from Uma. Can we use this mix for in situ applications?
Do you want to answer that, Kirk, or we turn that over to Jason?
Is Jason on the line with us?
Yes, he is.
Hello.
I think. Hi, Jason.
Hello. I take it you can hear me then? Good. So in terms of in situ applications, yeah, we can certainly look to do it. It suits precast really, really well. Some in situ applications, like I probably would say, if you're going to do a 200 cubic meter slab or something or other, that might be pushing things a little bit too far. But for smaller applications, then absolutely, there's no reason that it can't be used for that.
Yeah, it makes sense. Thanks, Jason. I think the advantage for precast, it's clear. I think especially the one-day strength that Dave highlighted, which is going to be important for the precasters. Thanks, Jason. Let's see if we have any other questions from the audience. We do have another question. Are you looking for more researchers, for example, research fellow or postdoc, to join your group?
I might answer that one. At the moment, we're fixed with the Smartcrete CRC project, but in the future and any sort of follow-ons from this technology, definitely, if the opportunity arises, we can be in contact and see how you can support that particular project.
Awesome. Thanks, Kirk. Sorry, Natalie. I'm having trouble loading the message. Do you mind
okay. I can read out the next question. We got a bunch coming through actually. They're coming in hot and fast. Are any major contractors jumping on board using this mix? Asks Craig.
We are doing extensive trials with a variety of different companies in Australia and internationally. And people are beginning to realize that this is a real low carbon offering and not just a lab creep, which geopolymer concrete has accused of being in the past. So yes, they are. Again, I can't disclose because of NDAs.
Thanks heaps, Dave. Would you like me to continue, Olivia, or is yours back online?
Yeah, mine is still. Sorry, Natalie, if you don't mind, if you could please continue. Thank you.
Of course. Okay, so Hushara asks, is there any possibility of reducing cover requirements?
What requirements, sorry?
Cover requirements.
Happy to jump in there, guys.
Yeah.
So basically, yes, there is. I mean, no one in the team is, necessarily a full durability expert, but as you saw from the results that Kirk showed, certainly the durability to chloride attack and sulfate attack, a lot of chemical attack, is significantly improved. So yes, there is a possibility. You'd have to look at each individual case as it comes about with the various results of the durability testing that we're doing.
Perfect. Thank you, Jason. Next question is from John Nicolaitis. Can it be adopted for 3D concrete applications?
I'll jump in and say I think it's actually very, very good for 3D concrete applications. Being able to get a workable concrete for the printing, and then having being able to dial up or down how fast the concrete actually sets and forms up would be a very, very good for 3D concrete applications.
Exciting. So next question is from Abhijit. In what form do you use the silica? Is it silicate of a metal?
All right, we use the activator, liquid and solid activators we use are silicates, and we use a variety of different ones depending on the effects that we want to create in the final product.
Okay, thank you, Dave. Next question is from CJ Wilson. What strengths are available? Does it require specialized labor to place?
Jason?
Thanks, CJ. Basically, you name the strength and we can work on making it. Would be the answer there. I've seen concrete's lower strength. I've seen, I think it was mentioned there, for 50 MPa plus. It's kind of a question of how much activator, how reactive are the precursor chemicals, or not chemicals, constituents. So yeah, any sort of strength theoretically possible, and we've done, let's say, 20 MPa up to 50 MPa, across the board would be what I'd say. As far as, do you need specially trained workers? No, you don't necessarily need specially trained workers. However, being a little bit different to Portland cement, you just need to be aware of how this concrete behaves, and maybe change your placing technique a little bit so that it can be placed and finished in an acceptable way. You probably, one interesting thing about this that I think will be, this is moving away from precast, but looking at the way that it sets tends to be fairly consistent, and therefore you get less likely to have people sitting around on cold winter days waiting for concrete to set. You can be pretty sure, based on whatever blend that you end up using, how long you're going to have to work with the concrete, and adjust your workforce accordingly.
Thank you so much, Jason, for answering that. I think this next one might be for Kirk, but feel free to jump in, Jason or Dave. Have you faced any challenges in getting the mix approved for use by clients or government bodies on construction projects? And that question is from Melanie.
It's a very good question, Melanie, and I guess that's what the Smartcrete CRC project is about. I mean, we're very, very happy to be working with Transport for New South Wales. There will be the opportunity to run some low-risk field trials with Transport for New South Wales, and there will be some recommendations made around codes of practice and specifications. This can obviously be adopted to other road agencies across Australia and also Ausroad. So it's work in progress, and we're very confident that the technology will find some application areas eventually within those particular government bodies. And in terms of clients, I might redirect that question back to Dave, just to give you sort of an idea of the different types of markets that he's working with, which we touched on earlier.
We obviously see three major market opportunities for this technology. Firstly, where there is a desire for the lowest form of CO2 emissions for a meter cubed of concrete. The second is in the precast market because of the ease to achieve the high early strength required. And thirdly, whereby there is conditions on use of things like mine tailings, whereby production of a particular mine site is controlled by the limits on the tailings dam. We can use those tailings in the manufacture of concrete to alleviate those issues. So we see those opportunities around.
Fantastic. Thank you, Dave. We have so many questions coming through. I'll do my best to work through them, but if we don't get through them, you can write into invite@smartcrete, and I'll drop the email address into the chat, or if you have a contact at SmartCrete, please reach out to us and I'll forward the questions to Dave or Kirk or whoever's relevant. So the next one is from Daru-san. Is Geomix available in the market now?
Yes.
Great. Would you like to add any more words to that, or should we just send him the webpage to check out?
No, we're ready to support new inquiries. We're working with existing customers. We have a policy of developing bespoke systems for customers so that it is what the mix design we are creating is specifically for the waste streams that a particular company will want to use and the final performance they want to use. But we're doing that for other customers now.
Sounds great. John Nicolaitis again is curious if you're willing to collaborate to develop 3D concrete applications.
Of course.
Yep. Okay. So, John, you can also reach out to Dave or myself or whoever's contacts you have to add further inquiries about that. Melanie again asks, are you manufacturing the activator in Australia?
We can source the activator in Australia. From a cost position, we are probably going to source most of the activator from overseas. There is a large availability of these chemicals we are using, so supply is not an issue.
Cool. Melanie again. Oh, sorry. Yes, Melanie again. She asks, did you have any issues with carbonation for durability? Jason?
So carbonation testing is certainly something that we're going to be doing as part of this project. And, you know, anyone who's seen accelerated carbonation test results with any sort of concrete that doesn't have a lot of Portland cement in it knows that the results sometimes come back sort of higher, I suppose, than if there is a lot of Portland cement concrete in there. Exactly how that impacts on the durability is, I suppose, open for interpretation. I've got my own views on it, but I'm not going to say it too much. But yeah, we definitely will be doing carbonation testing, and ideally, I think, and Kirk, correct me if I'm wrong, but we'd like to have the opportunity to test, you know, long-term carbonation in the atmosphere rather than looking at, you know, what a 12, 16 this does in a chamber.
Yes, that's correct, Jason. I think it's important to obviously have both tests going in parallel to correlate back to field behavior. And we want to run some longer term tests to fully understand the carbonation rate and also around modeling the buffering capacity. And I understand that that area at the moment is undergoing some revision based on some of the models that are out there used by industry.
Alrighty, thank you for that. Next question is from Jani, or Yanni, I'm not sure how to pronounce that. Although you have not completed carbonation tests, are you in a position to speculate about the outcome of testing? Unless you have ultra-low permeability, carbon dioxide will neutralize residual alkalinity supplied by the activator. If your activator contains alkali metals, the carbonation products become mobile and hence cause enhanced porosity. This is in contrast with calcium-based systems where the carbonation products are less mobile. Over to you, Jason.
I think all of that will be stuff that we probably do a little bit more research on. I'm not going to speculate too much as to exactly what's going to happen, but I think it's important. As I said before, it's important to understand how these systems behave in the atmosphere versus how they behave in an accelerated test environment, and then maybe work with industry as a whole to look at how we look at our standards and how we look at our specifications to be able to inform not just for geopolymers but for other materials as well.
Okay, cool. Thank you. So Peter asks, Kirk mentioned there are another 1.5 years in research. Realistically, how long will it be until something like this is available at Sydney concrete batching plant?
It's available now. We're doing further research to further improve the product and to test some of the durability areas that we haven't fully explored. But the product is available. We've demonstrated it in batching plants. So we're ready to work with whoever is interested in taking advantage of the improved characteristics of this technology.
Yeah, I'll say, Peter, by all means, let's have a bit of a chat about how we might be able to get something happening in Sydney. The materials that we have available in Sydney are very good for being able to use this technology.
Okay, cool. Sindhu asks, do you provide tech specifications to use geopolymer for projects?
Do you want to comment, Jason?
Sorry, that was technical specifications for how to use, was it? Sorry.
I'll just read it again. Do you provide tech specifications to use geopolymer for projects?
I think the easiest way to answer that is to say we can craft this to satisfy whatever specifications a project needs. I mean, within reason. If there might be some things that it can't do, but if there's this particular part of a project that we're looking at, and whether it's precast, whether it's even things like temporary works, this is where you get to do this sort of concrete and find out how it behaves and be able to use it in your projects. We can dial, as Dave's mentioned, we can dial up and down in terms of strength, in terms of set times and so forth. There's all sorts of different options. It's not necessarily Geomix, if I'm right to say this, Dave. Geomix is not a single mix. It's a broad range of concretes that can be produced using this Geomix technology.
It totally. What we found out is that the waste streams we use, they vary in the chemical composition, they vary in the particle size distribution, and they vary in the amorphous content. All those factors play into a change in performance of the final concrete. So we take the characteristics we see and we design the system to give the performance required.
That's really cool. Thank you, Dave. I've just, sorry, Olivia, would you like to, who is that jumping in?
Sorry, Natalie. I think Dave just, I guess, answered a question by Daryl's son, who asked about the raw materials variation. I don't know whether you've seen that one, but you skipped that. So it's about raw materials variation and other key parameters that may cause consistency of of variation between different batches. Yeah, I think Dave, you mentioned just now, I think answer this question. Am I correct? Yeah.
If I could jump into the consistency of a single raw material source is, I would say, quite good. I haven't necessarily got the data to say is it better or worse than ordinary Portland cement concretes, but certainly you get very consistent results. There's different sources of, slag will have different reactivities and different end results. So that's where, we offer that service to sort of dial in on exactly how your particular materials will work and how to make them work. But once that's done, I would say the results are, from what I've seen so far, and I've done a fair few of them, are pretty consistent. Once you have a material, it does the same thing each and every, mix and load that you do.
Thank you.
Thank you, Son, for that. So we've only got a few minutes left, so I might just do one last question. But before I read out the question, I've just dropped a couple of email addresses into the chat box. One of them is for Adam, who works for Canenviro, the guys that do the Geomix. So he's the business development manager, and you can reach out to him directly if you like, or you can reach out to us at SmartCrete too. And I will endeavour to follow up on the questions that we didn't get time to answer today that are in the chat. I will forward them to the question askers and the team. Okay, the last question is from Adrian Cahill. For the GWP values stated in the presentation, do they include data for the activators that is third-party verified, for example, sourced from an EPD?
So I can answer that. The particular one is from EcoInvent 3.10 database. Most of the data that you get from most materials other than cement in Australia is basically EcoInvent, whether you're doing Portland cement concrete or whether you're doing geopolymers. So yeah, it's the EcoInvent database. It does take into account the shipping from overseas, so that's been included in the calculations. But there is a particular line item in the EcoInvent that is essentially this material, and so that's what's been used.
Okay, thank you so much for answering that, Jason. Would you like to close this up then, Olivia?
Yeah, thank you, Natalie. Thank you for supporting the Q&A session. And I think that was a really informative and engaging session. And I think questions and interests from the audience today clearly shows the need for solution in this space. And I really appreciate the summary page that Kirk showed at the end. It was very clear in terms of how the project team measures the solution readiness level, and the next steps were clear as well in terms of field trials and standard environment. And like Natalie mentioned, if you'd like to continue the discussion or require more information, please reach out to Adam and the SmartCrete team. Again, a huge thank you to our speakers, Dave and Kirk, for sharing their expertise and their project work, and to all of you for engaging in today's session. And I'm sure we'll keep the conversation going on the COP platform, and I look forward to seeing you all in our next session as we continue to explore more innovative solutions in this space. So thanks again, and enjoy the rest of your day.